When Algos come marching home, hurrah, hurrah. When Algos come marching home, hurrah, hurrah. Happy Veterans Day, guys. As you can see, it's singing the Johnny Comes Marching Home, great Veterans Day song. And tonight we're going to be showing some really veteran algorithms. That's right. We finally get into NP completeness, the last and the hardest of all algorithm topics. And to really show that I truly respect the veterans in the Air Force, we're going to have airplane-related stuff tonight from my boy Victor Sun from Northeastern. So without further ado, here's Algos Intense Season 2, Episode 9, Veterans Day Special. Thank you for all the veterans serving for our country, and enjoy. As you can see right here, it's a very nice looking coloring. I made it very special for Veterans Day. Tonight's episode is sponsored by Expedia, which is actually very great because it talks about travel. And from a Hawaii trip, we use Expedia to actually get the best discounts for Hawaiian Airlines. Right now, with COVID slowly dying down, we can now enjoy travel again. A lot of topics tonight, so I'm not gonna go over all of them, but just to give you a heads up, it's a bit of a long episode, so bear with me. All right, great quiz question. What is the most famous non-deterministic NP reduction problem from the movie Imitation Game? With, Kate Winslet and good old Leonardo DiCaprio, all those guys from 2014. And while you guys answer, I'm going to be drawing myself a nice Turing machine, a nice example of that answer. All right, here's the answer. The Turing machine, that is correct. So back in World War II, Alan Turing made a great Enigma machine about encryption and decryption. And it was actually considered deterministic NP, non-deterministic NP, because you actually don't know when the Turing machine will end. So long story short, a Turing machine works as follows. You have input and you have output. And inside each machine, you have what we call read-write operations. In the non-deterministic case, the Turing machine basically cannot feasibly compute the final result. So basically it runs an infinite loop. And because it runs an infinite loop, it's basically non-deterministic NP. So it means there's no solution for it. And that's the reason why the Germans back in World War II could not easily crack down Alan Turing's machine. Very smart guy. So yeah, that's it for our quiz question. So yeah, what is NP completeness? Well, you've all heard about these things: SAT, knapsack, Hamiltonian path, traveling salesman, particularly that, subset sum, click, vertex cover, independent set, dominating set, and graph coloring. So all of them are called NP complete. So to give you a quick demonstration of what it means to be NP complete, I have myself a ring of circles that from my algorithms course with Professor Viola in Northeastern was pretty good. So here we have something called the P or polynomial time algorithms, all in P. And then here we have something called NP hard, which is all non-polynomial but hard problems. And then finally, in all of this, we have NP complete, which means the problem is without any, it's basically complete. Like there's no open-ended part of the problem. Like you solve it all in NP. Yeah, and that is basically it. That's what's like one of the most important drawings you'll find for NP completeness. And of course, the $1,000,000 question, does P equal NP? And if you guys can figure this out, you basically earn $1,000,000, because right now that is still not very possible, despite it being 2021, or if we're of quantum computing. So that is going to be the question of the night, if you guys can figure out P equals NP or not. Anyway, it's not NP hard. It's very easy to confuse the two when first studying this advanced topic. And how do we convert and translate one problem from another? Use reductions. Here's a caveat. This is not an algorithms class. We're not going to have a full-fledged proof of reduction. Just a general guideline of how to reduce with witnesses, certificates, etc., and how it works and how one should go about solving the problem. Quality over quantity as always. If we are to prove, we have to make sure both problems are in P. So yep, let's begin with our first reduction. But before we do, we have to do some terminology. So first thing is, what is a reduction? I keep talking about all the time, so I'm going to describe it to you. It's the process of converting an NP complete problem A into NP complete problem B, as denoted by A reduces to B. Some of these problems can be from or to reduced. A witness is basically saying something that shows both A and B in polynomial time, which means if you separate A and B, they can be solved polynomially. A gadget is if you have a subset of a problem instance that simulates the behavior of one of the fundamental units to a different computational problem, which means basically you can turn it into another form of the problem. And finally, to wrap it up, a certificate, something that certifies the reduction is complete, finishes reduction, or holds either true or false for one instance of A if in one instance of B. So here's an example. Reduction number 1. Independent set to click. So if you've never seen this before, don't worry, I'll draw a very quick example. These circles over here are called an independent set. Now you connect them over to like a triangle. This is called a click. So basically we're trying to determine which type of circles can be called an independent set. So we have these two, and you don't have a line here, that's independent set. They're trying to basically reduce ISP into a click. Now, don't get me wrong, this is something that even LeetCode will not cover. And honestly, it's not much on interviews. Whoa, that's weird. It's not something you cover much on interviews. But it is a good thing to know about for algorithms and actually for data science, because it'll teach you basically, can your problem ever be solved polynomially? So here's how the reduction will work. First, does the graph GC have a click of size KC given KC? And does GI have an independent set of size KI given KI? And then the witness will be, can the ISP be transformed into a click? And yes, you can, because you can connect the bipartite points in graph G as shown over here. And you can basically run a gadget, run a polynomial time program, a bipartite matching graph, as we've shown from the previous episode with Teen Titans. So once again, I'm going to show you a quick drawing of basically 3 circles again. Actually, 4 circles. And to make it bipartite, you can do the following. You can just do this and do this. That's all you can do. And maybe this. So you can definitely make a bipartite matching graph cover to check if it's in polynomial time. That's very easy. Just basically run a BFS and connect the nodes. And finally, a certificate. Independent set instance is true if and only if a click instance is true. So therefore, ISP reduces the click. And of course, to show I'm not BSing this thing, here is the YouTube channel that I used for reference. I'm going to show you quickly what this is. So I'm going to clear all my drawings here. And we'll watch a little bit of this thing for like a little feature film, basically. Yeah, so you can see this is obviously a very nice YouTube channel. It talks about reducing from independent set to click. So this guy over here basically gives a much more comprehensive reduction, which is obviously something we would be showing later in a bonus episode. But for now, this is good enough for the episode. So back to our slide. Reduction number 2, independent set to vertex cover. So this one's a little different. You guys have independent set, which is actually what we did before. But now you have to do what about vertex cover, which means the following. Let's say you have this graph over here and try to cover it like a vertex, right? So to cover every vertex like this. So vertex cover means no node is by itself, essentially. So here's how it works. Given a cluster of nodes k of I and graph gi equals vi ei, does g of I have independent set of size ki? And then of course the vertex cover given kv and gv equals v of v, e of v, does g of v have a vertex cover of size kv? And you have a witness of this as well. So if g of v equals gi, an independent set can be transformed into an instance of vertex cover if there's the same amount of nodes and connected edges between the cluster kv and the graph gi. So for this example, we can make a vertex cover because, for example, we can do something like this. A triangle is a perfect vertex cover. You have exactly 3 nodes here and 3 edges here. That works. Now, how about a trapezoid? That may not necessarily work because here you have 5 nodes and you have 6 edges. That will not work for the vertex cover. And to continue, the gadget is we need to find the difference of basically v of I, the vertices in the graph, minus the k of I, the independent cluster nodes, which means in this case, 6 minus 5 is 1. And k of v is basically a unique situation if it's 1. So basically, the entire graph is complete. It's a complete graph, which means that we run a polynomial time check for any nodes that are not in the independent set when compared to instance of vertex cover. And therefore, we have a certificate. G of I is independent set with size k if and only if G of v has a vertex cover of size kv. And of course, the same YouTube video, I'm not going to show you this time around, but that is basically how it works. One little note. When you do a reduction, please do not do the following. Do not mess up the direction of reduction. This is something I messed up in my homework for algorithms at Northeastern, and I actually messed up as well when I was doing a clustering thing with Dell as well. So do not mess up the direction of the reduction, or else you're going to have a hard time. And you even have a hard time like trying to get past the West Point military physical exam compared to this. It is not for the faint of heart to try to undo or get reverse a bad reduction. Not cool. Finally, we got satisfiability for the reductions. So what does it mean to be satisfiable? Well, let's say we have a nice looking clause here. And of course, to get into a little bit of circuits, feed my boy Alex Moisey and B. Rumi Graham. And also just to simply, show I love to use hardware. Here's some circuits I can build. So here's a little XI circuit I have, coupling facility. You have another X2 circuit here. And you have a not X3 circuit. So this is gonna be a little bit smaller X3 and a not symbol, like a not type of gate, a not gate. I'm no circuit design buff, but I generally know how the circuit works. So this symbol means not, by the way, for logical Boolean. So quick quiz, if this means not, then what does this mean? And correct. You've definitely reviewed your Boolean logic. And what does this mean? Or correct. And generally that's about it. We don't need any more. We could go over this, Zor, but that's sort of overkill. I don't want to give you guys basically a Boolean logic thing. That was actually a bonus algorithms episode we did before. So we don't really worry about that. So yeah, 3 satisfiability clause. Given a clause phi of I for I literals, does phi of I have a satisfiable arrangement of gamma of I independent Boolean clauses? And then for sat, given an independent Boolean clause, gamma of I for I variables, does gamma I have a satisfiable agreement of phi of I clauses? So that gibberish basically means like, can we put the clauses together and make it true? And then of course a witness. We can replace each clause with a 3 set to set if it's satisfiable. This will be a Boolean algebra. So for example, we have something crazy like this, x1 and x2 and not x3. And then the the gamma becomes x1 is some variable a, or x2 and not a. Well, look at that. A's are gone. Sorry. Oh, well, look at that. A's are gone. Oh, yeah. Logic is making me do some stupid things here. So yep, A is gone here. So you can see A's are canceled out. And then B and not B also canceled out. So of course, A and B went to cancel culture. So that basically makes the same exact thing as x1 and x2 and not x3. Boom, there we go. So the gadget shown in the next slide is very big and very hard to understand, but basically tells you can't connect the same type of negation node. So for example, you have like another node, x1 not here. You cannot connect these two. This will end all life on Earth. This is not allowed. So that is not allowed. And then finally, for a certificate, you have a phi of I have a satisfiable arrangement of I clauses if and only if the gamma of I Boolean clauses are all satisfiable, which means basically all of them are true or false. There is no like true, false, true, false. It's either all trues or all falses. And this proof is complicated, so I'm going to go to Mellon, Carnegie Mellon that is, and show you guys a good example of it. So here's yet another link we can take a look at. And I'm going to get rid of this gibberish over here. So I normally don't look at too many lecture notes outside Northeastern, but this is good for you to understand. So satisfiability here from Carnegie Mellon is very interesting. As you can see, they do a much better job than I do talking about each type of reduction. And there to give you the warning I just told you, you should reduce the known NP-complete problem to the problem you're interested in. You will mistakenly do this backwards sometimes. Please don't. So yep, that is it for that part of the slide. All right. And now we talk about the gadget. So as I told you before, you cannot connect, for example, x2 and a not x2, or you cannot connect an x1 to not x1. That is not allowed. However, you can connect adjacent negations. You can connect, for example, x3 to not x3 here. This is adjacent. That's perfectly fine because you're given that in the satisfiability clause. So the blue lines basically represent proper connectivity. We do not connect any ordinary false and true nodes. That does not work. These are not adjacent to each other. In addition, you have the most basic form of satisfiability within NP completeness. And the clause symbol need not be the same for the parentheses. All right, guys, let's take a quick breather, a quick break, and then we'll go to a priori. Cool. All right, hope you guys got a little bit of time to think about that. So before we go to a priori, here are some other reductions that I think you guys all love and know. A LeetCode classic, traveling salesman problem. This is NP complete. You can try to do it in DP, dynamic programming, but I wouldn't recommend it. It's too hard and it's just not worth your time. There's a Hamiltonian path and Eulerian path. You also have dominating sets and weighted knapsack with replacement. And of course, my man, Eric Domain from MIT, you can have Super Mario, yes, turn into satisfiability and much, much more. So once again, the point is to show you not how many times to reduce, but how to reduce itself. Now we're going to talk about a priori, plain stuff. So consider the following data set. Let's say we want to fly anywhere in this world, well, post-pandemic world. I'm going to draw a nice looking world over here, because I like to draw. So there's a nice big circle. Let's see, draw America over here. That's looking America right there. Then you have Mexico, then you have South Latin America, and you can see I'm a bit of a liar. I don't know how to draw the world too good. But this is basically the world we're drawing here. You're drawing the world in a very 5-year-old approach, but it is at least a world worth looking at. And you have the ocean, blah, 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 yeah, yada, yada. So we get 3 main types of boarding flights: first class, business, and economy. So you can see shown in a plane, and I'm going to draw a very good looking plane here. Usually shown in an airplane, right? When you board an airplane, you have generally 3 sections. You got the first class over here. Then around the wings, you got yourself the business class. And all the way in the back, you got the economy class. And I went to Boston Logan for the Hawaii trip and basically told me that they're in zone 4. Sorry, they're in zone 4 over here. And here are zones 1 to 3. So why am I telling all this? Well, because you have to worry about that for a priori. You have to worry about priority. Priority matters. So we get 3 main types of boarding flights: first class, business, and economy. There's a flight attendant thanks to collaboration to a data scientist provides us the following association rule table. You have first class in one column, business, economy, business, and the economy, business, economy. So take one good look at these pictures and they're going to be gone now. So what do we measure for a priori? We measure something called support. So the fancy math could be searched on Wikipedia, but basically means the support of a particular class is like how many instances of class do you have in a subset over total number. And we're trying to find out how many times there's business in that table. Well, if we look previously in the table, there's only 3 business classes and there are 5. That's right, there are 5 related elements over the table. So that's 3 over 5 or 0.6. Next, you got the following. You got confidence of x to y. Wait, actually, no, I messed up. My apologies, it's actually not 0.6. I messed it up. And this is the first time Algos intend because I was not being careful with my math. I messed it up. It is 0.5. So yes, I do botch and make mistakes sometimes. I'm not a perfect person, I make mistakes. Just learn from your mistakes. So it is 3 over 6, yes. Next, confidence, you have x to y. You have supply x union y over supply x. So in really quick Venn diagram theory, it means basically this. You have x, you have y. You have x, you have y. So essentially, you're trying to determine what is the union of x and y. So for example, you're trying to basically determine all this stuff over here over the x over here. So x union y is the same as x disjunction of y and not y. That's just basically logic for you. Okay? And for that, it's 0.5 over 0.6, which is 0.83. The lift is a little complicated. So you have x union of y over the disjointed sets of x and y. So since I calculated finally correctly now, it's 0.5 over 0.25, which is 2. A good lift value indeed. And finally, conviction, you have 1 minus supply of y, minus support of y, and then 1 minus confidence of y, which you have to tell based on substitution. It's pretty obviously going to be 0.5 over 0.4, which is 1.25. Great. So here's yet another reduction. I'm not going to show anything, but talk about it. It is possible to reduce from independent set to a priori. So independent set is given GI and GV, V of V, E of V is an a priori item set of size I with up to V1, V2 up to Vn frequent item sets. What do I mean by frequent item set? I mean by item sets that are basically with greater probability than 0.5 showing up. And for a priori, given item sets of frequency V1, V2, Vn, there's an independent set of size I for each given graph G of I and G of V, V of V and E of V. And finally got the witness. The operator can be transformed into basically an independent set of size if the frequent item sets is just 1. So what does that mean? So let's say, for example, I got a nice looking a priori set, A, B, C, D. You can now turn it into separate sets, A on B and C of D. And that's basically all you got. That is your gadget. That is basically your witness. So you can basically turn this into like a subset of different elements with your witness, independent set. And the gadget is all pairs of frequent item sets can be solved in polynomial and creating the clusters of independent sets. And let me show you a quick example of gadget. A, B, B, A, ABBA. So A, A, B, B. There you go. And then certificate. For V1 to Vn data sets, the a priori item set holds true for each independent set of up to size V of I, where I is less than or equal to n, if and only if there is a given independent set of size I less than or equal to k. And more explanations in the Wikipedia, which you can search for yourself. So long story short, you could basically reduce anything to anything as long as they are both NP complete. And now we got ourselves the problem. Finally, after almost 27 minutes of talking about NP and a priori, we finally get to the problem. So with the problem, I'm just going to really briefly talk about it. We're just 2 months away from the end of 2021, which means in business speak, we're in Q4. False company Apriori Co-op, a subsidiary of Expedia, has tasked us to do the following. Given the following data set from Kaggle, use classification machine learning techniques, such as a priori and FP growth, and association rule data mining to classify tier rank, the S tier, A tier, B tier, C tier, the best flights for 2022, given 3 main features: duration of the flight, food and drink quality, and satisfaction of each flight. Notice this is a Kaggle data set, so I have to pre-process a little bit before I apply the a priori. So this is actually very similar, but not exact, of my CS62440 data mining course graduation project for my master's cum laude. So hopefully this thing will show you how Kaggle works. I'm just quickly give you a little demonstration of the data set. There you go. So Kaggle is a free website for data scientists to use. It's a pretty good data set, this thing. So you have basically Investico, CSV, you got, gender, satisfaction, customer type, blah, blah, blah. The trouble with this data set, as you can already see, is there's some null values, missing, invalids and stuff, which means it's not very reliable. So guess what happens first with the data? Just like brushing your teeth, you have to first clean up the data and then get to floss it. So we're going to now brush our data set a little bit by pre-processing some things. So pre-processing, we read the CSV using CSV reader in Python or anything else in Java. You eliminate the NaN or null values by dataframe.fillNA. Usually we tend to eliminate NaN null values featured together, but for this data set, we may not necessarily get rid of all of them. We'll show you in episode 10 what to actually get rid of. And then just some very basic feature engineering, make some changes to the data set. Make sure we have a copy of the data set before you do anything. This is a mistake I made in my graduate school work with data mining. We did not make a copy of the data set with me, actually advised my 2 teammates. We had to basically redo the project somewhere in mid-semester. Do not make that mistake. Make necessary changes to feature columns, and we write out to the appendix data frame using d of the head. So what does d of the head mean in terms of a data frame? Well, think of a data frame like this, like a rectangle. I have a subset of it called the head. A subset of it called the head. So just like a stack, this is not necessarily all of the top values, but rather is the top values in memory. So usually the head, which means the top 10, usually when it says d of the head. However, you can change it to be top 5 or something else. Even top 1, the best of the best. But usually means top 10 for d of the head. And also you can remove any not useful features to avoid dimensionality problems later on. And this is what's called the curse of dimensionality. So 1 dimension is fine, right? 2 dimensions is fine. 3 dimensions is getting a little crazy, but also still very, very fun. And I'm not going to draw this, but the 4th dimension, this is where it gets a little ugly. So eventually it gets to the point where you have just too many dimensions and it gets a little bit crazy. So you want to avoid the too many dimensions. If you have dimension to the power of r, where r is basically anything close to like infinity, the problem becomes NP. You can no longer solve it polynomial time. And this thing is basically a waste of time. So please avoid something called the curse of dimensionality. This is something that data scientists and computer science alike do not want to have. Avoid that. Moving on. You apply SMOTI. So I talked about SMOTI a lot from previous episodes. Finally, I'm going to show what SMOTI means. So wicked is a simple example. Dot, 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 dot. And then, for example, red dots. Dot, 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 dot. So for this looking cluster here, without applying SMOTI, do you think this thing will be easily balanced or not easily balanced? Looks terrible, right? Looks like crap. Looks like basically Starfire's pizza went into a microwave and got blown up. Terrible. So this is a very crappy classifier. However, you apply SMOTI, this gets a little bit nicer to look at. You have 2 separate things, a majority class and a minority class. The majority class is all in blue. It's just dot, 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 dot. And then the minority class, a little bit less, it's just a bunch of red dots here. So generally for SMOTI, you want to get around a 70 to 30 ratio. You know the ratio I mean, right? Like likes to comments. Majority over the minority. If you get 50-50, this SMOTI is bad. You can't use SMOTI. From our project, we got a little bit unlucky. We got around 60 to 40, I guess, for our project. So apply SMOTI, which is called synthetic minority oversampling technique. It's generally used to balance classification. We'll use 3 main models to do it: decision tree, logistic regression, and clarity boosting, so just like my project. I want to get AUC value of 0.7. So remember, so you can see why this episode is the finale, right? We're going through everything in Algos in 10, season 2. So here is the AUC curve. Now, of course, the greatest, most amazing AUC curve is just straight up a beautiful looking hyperbola of 1. And the crappiest possible is this one, 0.5. What does 0.7 look like? It's a bit of an oblong hyperbola. So it's like almost hyperbolic. I'd say probably y equals, I don't know, 2 over x or something like that. So it's nearly hyperbolic, but not quite. And we want to get a target AUC value of 0.7, which is the blue line over here. Up next, we've got something called random undersampling, to randomly delete examples from the majority class. So we want to mainly use to naively rebalance the class distribution. And we'll note this time get a 60-40 ratio for majority and minority classes. We use the same 3 models and get an AUC value of 0.7. An additional caveat, to make sure there's no duplicate data, we basically remove duplicates. However, for random undersampling and for SMOTI, you gotta be very careful with one thing called k-fold selection. So k-fold selection is a very important concept in any modeling you do in algorithms and in data science and machine learning. I will talk to you later in episode 10 what it means, but generally means you have to do a selection of iterative selection of how many times you run the model using generally 10 folds. It takes a long time to run the algorithm. They'll make your model just that much more efficient. And of course, talking about a priori, we know it's very similar to basically a subset sum. So we're going to check Wikipedia for this very quick. So this does a fantastic job talking about a priori. So look at example 2. You have item sets over here. You basically determine the item sets into number of occurrences. You see 3 times of 1 from the first 3 item sets, 6 times of 2 from all the item sets, and you continue doing that up to unique item sets. So you cannot have any more frequent items. Then you basically have up to the triplet, which is the most you can have for item set. And the main caveat for this one, of course, the main caveat is to get clusters for the flights to make a classification model to solve the problem. We'll basically apply the support, confidence, lift, and conviction, each in a separate Python function for episode 10. Coming up next, you got FP growth. This only requires basically two things: a trie data set, which is like a tree, and you have a frequency pattern table for each frequency of the flight features. You create a header table as well, which counts of each frequency. So let's give a very quick example of this. Let's say Hawaiian Airlines, Hainan Airlines, United Airlines, Hawaiian again, Lufthansa Airlines, and finally, I don't know, British Airways. So with these different airlines, what can we do? Well, we can do the following. You can first cluster them based on their properties. So you have Hainan Airlines and 2 Hawaiian Airlines here. We have United Airlines, Lufthansa, and British Airways. They can cluster them again by basically 2 versions of Hawaiian Airlines, HAI, which is Hainan Airlines, and then UA, LH, and BA. And that's basically it for the cluster. So you want to build a pattern that can analyze with using classification, algorithms, and modeling. It's a lot, isn't it? Well, episode 10 will make all this gibberish so much clearer for you. And just like a plane ride, just like a takeoff, it's meant to be, unsteady. When you get to episode 10, basically landing is a nice, gentle landing to our destination, which is the end of the season. Finally, we got the beautiful ROC curves. For each of them, decision tree, logistic, and gradient boosting. For both SMOTI and random undersampling. You can use matplotlib to do this. And generally, you want to have 0.7 AOC, but I don't want to be a genie. We're not guaranteeing anything. And finally, ROC curve will be compared to a perfect AOC classifier of 1. So as I mentioned before, why it's called a grand finale, putting everything together, it's becoming like a semester project type of tough. So it's meant to really challenge you if you had to do this all by yourself. Me, having done this already, have some starter code to work with. But this is something I would probably expect like a semester project to do if it's a real problem to solve, not just only a toy example. So then talk about heat maps, very common heat maps, confusion matrices, some linear regression. So quick review of linear regression. You have an XY plot here, and you have a bunch of dots over here. So what does this mean when the line goes up like this? It's positive correlated. But let's say, for example, some crazy guy, drunk and whatever, decides to choose a line like this. It's not necessarily a bad fit, but it's a bad linear regression model because you don't cover all the lines. You want to have it nice and correlated for all the lines. You'll see later why we use matplotlib to do this and use heat maps to double check our work. And they may not be very accurate if features are positive correlated. So you have to be very careful which features you use. So that's why, once again, have to be very careful pre-processing the data. And finally, talk about clusters. We basically make some very nice looking clusters. We avoid bias and sampling. We'll do something very similar from the Team Titans problem, incremental clusters of 1, 2, 3, 4, 5. If necessary, to 6. I personally predict the clusters won't go past 5 in this one. And they'll be put in separate features, not mixed together. So please do not use GMM for a priori or FP growth. It will screw you up. Use PCA and SVD, always. We'll get a solution for clustering to work once we hit the elbow rule, which I hope you remember what that means. A certain number of clusters given some features, you can approximate that. And then finally, we'll have the nice tier rank of all the best flights post 2022. So yeah, that's it. That's the problem. But of course, we're not done yet. We could talk about future work. So maybe if I had more time, like for example, like a sabbatical from my Dell job or another semester, I could just pre-process some more data, do more classifiers, like neural nets from all from episode 1, or even TensorFlow, the LeBron episode. You can also combine some data sets. You could clean some more data more rigorously. You can do like some categorical data set work. But honestly, it's just too much. Like, to quote the meme, I don't have time for that. Like, it's one episode for 50 minutes, and it's just too much to do for one episode. So that is, I think, a very good starting point to what we can call an exploratory analysis of classification modeling. So finally, preview of the finale of the season. We have a gigantic, huge notebook that's going to be over 2,500 lines of code. So all this Python stuff, all this gibberish is going to be shown in Python for 1 hour, 1 hour finale episode. Definitely worth my Thanksgiving. There'll also be a Selenium with Java bonus for some processing clustering nodes, and Python as well, with some cool WebDriver applications. Basically show a Heroku website, show some clusters. Those will be separate from the notebook. I just want to say thank you for a great season of Algos in 10, season 2 with Jason Liu. It's been a really, really long season ever since June. I think back in season 1 last year, I was trying to juggle my Northeastern work, my co-op and everything to get everything done in my summer course with algorithms. But I think with my Dell work now, I'm trying to get more appreciation of like all the algorithms. Thank you so much for my subscribers, for everybody, and everybody who really loves computer science applications and all these great things. Continue to be optimal in your choices. So yeah, see you guys in 2 weeks at Thanksgiving for season 2, episode 10. And if you have not subscribed and liked by now, what are you doing with your life? So yeah, enjoy Veterans Days, guys, and honestly, continue to stay safe during this time. Thank you very much.